We've got Alex and Stuart, so we can have a class. Not only that, but we've got Ashley and Nicholas. We got some of my best students here. Good deal. Excellent. See if this is all right here. Yeah, that looks pretty good. Wednesday the 18th. Yeah, today's a very special day for me. It's my 53rd wedding anniversary. Number 53 today. I was married 18th of November, 1967. It was before some of you were born.
Congratulations.
Thank you. Thank you. Well, let's get going here. Do you have any questions before I get started on our topic today? Any questions? I don't hear any questions. So, well, let's see where we are. Now we had our exam, and I graded it, right? Yeah, I think I did. You guys did okay on it. Yeah, everybody did it. Got grades in the book here. Some are pretty good grades. Good going, you guys. Okay, and homework. Let's see. Let's see if there's any homework. This is the 18th. Yeah, it looks like homework number 27 is F 19.5. It's due the 21st, which would be, gee, I don't know, what's the 21st? That's Saturday, yeah, due Saturday. So there's some homework you can do. That won't hurt you any. And then we'll have a final one of these days, take home final. That's December 7th. That's Pearl Harbor Day. December 7th. Now, when is that? That's, well, it's not next week, because that next week's Thanksgiving. In fact, a week from tomorrow is Thanksgiving Day. And then you have, well, we'll worry about that when we come to it. Okay, let's get into our topic for today. And it is impulse momentum, only it's angular impulse and angular momentum. Let's refresh your memory. Did you know we study four ways of solving our problems? There are four methods that we use in this class in the study of dynamics. See, dynamics includes motion and forces and moments. And we have four different methods. I bet you guys could, any one of you could rattle off those four different methods. Let's go to one of my excellent students here. Stuart, I'm always picking on Stuart. Stuart, do you remember any of our four methods? Probably drawing a blank right now, Stuart.
Yeah.
I'll give you a hint. One of them is the most important equation in the course, and one of them is the second most important equation in the course.
Newton's second law and the work energy theorem.
Yeah, good going, Stuart. Proud of you. Newton's second law and the work energy theorem. Now, this is shorthand for it. Now, I want you to really try hard now, Stuart. There's two other really important tools or methods. Can you think of one of those? He's drawing a blank again. Here, I'll give you a hint. Stuart, there's a whole bunch of equations kind of like this. V equals R omega. A equals something. I don't remember what. Yeah, well, this will do it. There's just a whole pile. What do they call that method, Stuart? Where you use those equations? Uh-oh. Anybody? It's the first method we studied. We studied it. What do they call that? Nobody's going to help me here. You're just going to leave me twisting in the wind here without any help. Come on now, let me pick on somebody. Nicholas, you come to the rescue. What's the name of this one that there's all these equations here, like this one here, for instance. Nicholas, what do they call that method when you use these equations? What do they call it? Nicholas, help. Help, I'm drowning.
I wish I could help. I don't know.
I'm sorry, what?
I don't know.
I'll give you a hint. It starts with K. Second letter is I. Nicholas, you can do this. The third letter is N. Come on, Nicholas. The fourth letter is, I think it's an E. I'm not sure about the spelling. Do you have it yet? Nicholas is thinking. He's not going to help me. Ashley, come to my rescue. What is this important method that we've studied that uses all these equations here? What is the name of it, Ashley?
Kinematics?
Yeah, it's kinematics. Come on now. Nicholas, you knew that. Well, there's a fourth method, and we've actually studied it. It's called impulse momentum. We've studied it. It's called the impulse momentum method. We have four methods that we use in this class to solve dynamics problems. And if you get stuck, oh, I don't know what to do, oh, I don't know what to do, maybe I should switch my major to psychology. Just go back and try one of those four methods and maybe you'll figure it out. Don't give up. All right, now the topic today is the impulse momentum method. Only see, we studied it before with translation, going in a straight line maybe. But see, today it's under rotation. There's a rotational. See, there's linear impulse momentum, and there's angular impulse momentum. And today we are studying angular impulse momentum. So let me write the equations here. Here we go. You got some homework there. We're in chapter 19. Here, let's review and put the linear impulse momentum equation. We'll write it down first because you've had it before. And it goes like this. It's really a vector equation, so you can put vectors on it like that. And this term here is called linear impulse. That's the name of that term. That's called linear impulse. And these here, that's called momentum. It's linear momentum. That's the final, and this is the initial. See those terms on the right side are well, the plural of momentum is momenta. Those are momenta. But today we're going to study the angular impulse momentum equation. And it's angular impulse and it's angular momentum. It's still impulse and momentum, but now we're studying angular impulse and angular momentum, and it goes like this. And this I thing here, we've studied that. It's called the mass moment of inertia. You've seen it before. It's in Newton's second law for rotation. Oh, yeah. Okay, now let me show you where this came from. Maybe I can show you where that came from. Let me see how I forget how to do this. Let me see what the book does to show you that. This is chapter 19 now. We're entering our last and final chapter here. You know what? Not much school left. I know you're sad about that. Okay. Trying to find where. Yeah, here it is. It looks like they do it on page 523. I'm trying to remember the quick way to show you how to do this. Well, I can't remember how to do it right now. Now we need to put a little G right here. Tell you what, let's work some problems, and then if I can remember how to derive that, it's derived from this. You take this equation here and you do some calculus and some algebra and you come up with that equation there. That's what it amounts to. Yeah. I think what you do is you take the cross product. You take a cross product. And here you go R cross F. And over here you go R cross MV minus an R cross MV. You take a cross product and then you multiply by time. Now, just a minute now. Let me show you that another time. Right now, let's just work some problems. We got the equation here, and we can derive it for you a different time. They tried to explain it on page 523. It's right there. You can, tell you what, read it yourself. And now let's work problems. Okay. You guys don't want to be bored by a derivation right now anyway. You just want to know how to do this stuff so you can go on to OSU or wherever and know what you're doing. Now, our first problem for today is, we're going to do a fundamental problem. It's F19.4. We're going to do F19.4. Now, let me find it. F19.4. Ta-da, I found it. Okay. Ooh, you got two gears here. You got kind of a smaller gear and a bigger gear. There you go. I don't know if I did those to scale very good, but I tried. This has got a radius of 0.1, and this is 0.2. 0.1, and this one here has a radius of 0.2. I am on page 532. And we're going to get the moment of inertia for each one. Now, you know the equation goes like this. The moment of inertia, they both have g's. They're different. The g, that's the center of gravity there. That one's there. This is equal to the mass times, what do they call that thing? The radius of gyration squared. And they give it to you. This mass here is 10 kilograms. Radius of gyration is 0.80 meters squared. Well, that's for A. There's an A and a B. We're going to call this A. We'll call this B. The moment of inertia for A about its center or centroid or center of gravity is that. And the moment of inertia about B would be, see, they said this was 10 kilograms. What's the other one? 50. This one's a lot heavier. It's 50 kilograms. And it's going to be 50 kilograms times 0.2 squared Okay, I'll shut up for 1 minute. I want you to get those moments of inertia for me. Go ahead, do that, please. Okay, your time's up. The moment of inertia for body A. Let's go to my friend Mark. Unmute and say hello, Mark.
Hello.
Hey, Mark, what'd you get for the moment of inertia for gear A?
0.064.
That's what I got. Good going, Mark. And what I got for B was, double check me now, 1.125 kilogram meter squared. If anybody got that, say uh-huh.
I got 2.
I also got 2.
Did I do it wrong?
I think it's supposed to be 0.15 meters squared instead of 0.2.
Oh, thank you so very, very much. You're absolutely right. And I'm absolutely wrong. See, it helps to have smart students. Now, let me see if I can do this right. Hey, how about this? 1.125. You guys feel better now?
Yes,
No,
sir.
wait a minute. That's what I got before, wasn't it? But that is right, isn't it?
Yes.
Yeah.
Ah, good. I feel better now. All right. Well, now we're doing okay. Thanks to your help. Who was it that first spoke up? Who was that?
That was Stuart.
Stuart gets a big fat thank you point right there. Good going, Stuart. Now it's time to put the red stuff on here. Well, I know there's weight, but I don't think the weight matters much. You know, there's a weight here, but see, there'll be a force going up here, equal and opposite. Do not call it a normal force. Normal forces are forces associated with surfaces, like a ramp or a plane or a road, maybe. This is the force on that, it's spinning about a, what's the word, spindle or central shaft there. And the same thing here. These will be smaller. There's a weight here and a force going up, but those just cancel out. I'm not interested in those. I'm just not even going to worry about them right now. But I tell you what you do have, you have a couple. They said there's a couple. It's a spin, it's a twist. So it's a moment. And that moment is 10 Newton meters. It's 10 Newton meters. Is trying to spin that gear clockwise. Well, you understand that's going to make this gear go counterclockwise. This gear is going to spin clockwise, but this gear is going to spin counterclockwise. Now, since they have different radii, this one will spin faster. In fact, it will spin it will spin, this will spin twice as fast. The omega of gear A will be 2 times the angular velocity of gear B. And I'll be glad to explain that if anybody wants me to. Does anybody need me to explain how come this gear goes twice as fast as that gear? Anybody? See, you don't need me to explain that because I've explained it to you already. And since you don't need me to explain it, that means you understand it. So I can call on anybody in this class and they can explain to me how come the angular velocity of this small wheel is twice the angular velocity of this big wheel. Remember my story about the big dog and the little dog? Did I tell you guys that? The little dog and the feet go real fast. Boom, the feet go real fast if you watch a little dog go down the street. But a big dog, blah, 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 blah. It doesn't wiggle its feet and hindquarters and forelegs. It doesn't have to. I could ask any one of you to explain this, but just in case, I'll go back through it. See, these have teeth. It's kind of hard for me to draw teeth on these gears, but those teeth, you want them to go at the same velocity. You don't want these teeth on this gear here going faster than the teeth on that gear there. They'll break off. The little teeth, they'll break. You want them to mesh and go the same speed. Well, remember how it works. V equals R omega. So VA is equal to RA omega A. VB is equal to RB omega B. Well, if you want the velocities to be the same, set them equal. And so the omega of A will equal the R of B over R of A times the omega of B. Well, see, this here is 2 to 1. So you get 2 omega B. Omega A goes twice as fast as omega B. So we got that figured out. And there's the explanation. It's based on that equation right there. You could have told me that. I could have asked any one of you guys that. And you understand it, I hope. Okay, now let's do our, what do they call, impulse momentum equation, shall we? Here we go. Now, how does that equation go? Let me write that. You go the integral of all the moments, and now you have to do all of them. That's the catch. Is equal to that. There's your equation right there. These are actually vectors. Okay, now here's the tricky part. There's an external moment, like somebody with a tire iron that's trying to twist this gear. Or you might even have a small inner pulley with, you know what I'm talking about. You could have a hub here with a pulley connected to a motor. And the belt is trying to drive that body A clockwise. There's all kinds of ways you could get that moment. But anyway, you have that moment. trying to twist it to the right. But see, it's got teeth here, and those teeth are meshing with body B. And so there's going to be a force. There's going to be a force on A from body B because the teeth, when those teeth mesh like that, there's going to be a force. And the thing is that force be going up? Is the force on body A going up, or is the force on body A going down? Let's ask one of my excellent students. Now you got a 50-50 chance of getting this right. And I don't want to pick on Stuart. He just helped me. Shane, unmute and say hello, please, Shane.
Good morning.
Yeah, good morning, Shane. There's a force from the teeth on body B acting on that gear A. Is that force on A going up or down, Shane? Up or down?
I'm gonna go with up.
Okay, Shane's going to go with up. Now let me think about it. You know what? I think Shane is right. Shane, you go to the casino. No, don't go to the casino. They'll just take your money. But you got that one right. Good going. Now the reason why it's up is when this wheel turns clockwise, it's going to put a force on B going down. There is a force on B going down, but see, there's a Newton's third law, equal and opposite force of B on A going up, and it's going up. I don't know what to call it. Why don't we just call it F? That's a nice name. We'll just call it F. But the force on A is going up, but there is a force on B going down. Okay, well, let's write our equation then. Here we go. We have 10 Newton meters. I'm going to write this equation. 10 Newton meters. And the time, read the problem. They said the time is 5 seconds, so you have to multiply by 5 seconds. We'll write all of our impulses clockwise. See, this is called an impulse. But there's another impulse on body A, and it's going the other way, because Shane says it's got a force going up. That's going to go counterclockwise. So that's going to oppose that 10 Newton meters times 5 seconds. And trouble is, I don't know what it is. It's just F, but you have to go times 5 seconds. Hope you can read my writing. Now over here, we've got I of G. Well, it's I of A is what we're talking about here. We're doing body A, the gear at A is what we're talking about. And it's 0.064. 0.064 kilogram meter squared times, I'm just going to call it omega A. It's minus 0. It starts at rest if you read the problem, so they don't have any starting omega. It's not turning. It starts from rest. Well, we got a nice equation now, but it's got 2 unknowns. We don't know those 2 unknowns. What are we going to do? Change our majors? Nah, we're not going to do that. We're going to write the impulse and momentum equation for body B. Here goes. I just need some room here. Let me box this one up. This is a nice little equation. We're going to keep it. But we're going to do the same equation, but for body B now. Okay. Now on body B, they don't have a 10 Newton meter moment acting on it, but they do have this force. But wait a minute, that's the force on A. The force on B is going down, isn't it? See, the force on B is going down, and it's equal to, the moment is equal to that force times is it 0.2 meters? Yeah, 0.2 meters. The force time, that's the moment. The force times the distance. See, this is 2 meters. But the force on body B is going down. So that's going to be a counterclockwise moment, and that's it. There's only that one. Don't forget, times t, 5 seconds, equals the moment of inertia of B. That's 1.125 times the omega of B minus 0. See, it starts at rest. Here's our other equation. Now we have 2 equations. Unfortunately, we have 3 unknowns. But see, we can write this omega A as 2 omega B. Why don't we do that? Stick 2 omega B in there. And now we have 2 equations and 2 unknowns. And I wish it wasn't so ugly, but I don't know any other way to do it. You have to solve that. It's an algebra problem. But we can do it. We took algebra. Well, I did this earlier, and I got an answer for, here's what I got for my answers. I need some room here. I'm going to spare you the 15 minutes it would take me to solve those 2 equations with my limited algebra skills. But here's what I came up with. We can see if it works. I got the angular velocity of A to be 144.8 radians per second clockwise, and the angular velocity of B to be 72.41 radians per second counterclockwise. See, this one's clockwise, and this one's counterclockwise. And the F, I got that F to be, see, there's an F in there. There's an F in there. We can solve that too. I got that to be, just one tiny minute here. I got that to be 81.45 newtons. So we got all of our unknowns. Now, what did they want us to solve? Let me read this. Determine the angular velocity of gear B when, well, here's what they wanted right here. This is the answer. Now look in the back of the book and let's see how we did. This was fundamental problem 19.4. And so we're going to go back here and we're going to look it up. Fundamental problem 19.4. They said, $72.4. Here's what the book says. The book says 72.4 radians per second. That's their answer. Well, that's what we got. Yay, we did good. 72.41. Radians are dimensionless, so all we have is just somethings per second, but they're radians per second. So we did great. Now I skipped the algebra, but I know you guys can solve those two equations. Do you have any questions on fundamental problem 19.4? Well, again, if nobody speaks up, I just assume that you understand. I assume you understand. Okay, well, here, I'm going to erase all this if you got it, and we'll do another one. Okay, here's your chance. Speak up. You're happy with this? You guys are awfully quiet. Okay, well, we conquered that one. Let me tell you a dirty little secret that might help. On these problems. If you run into a problem where they give you time, if they give you time, then the method that is easiest, all our methods work. Remember, we have 4 methods, and you could write down those 4 methods. Bam, 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 bam. You could write them down for me because you know we have 4 methods that we study in this class. If the problem is they give you time, then you want to use the impulse momentum method. It's easier. If they give you distance, then you want to use the work energy method. It's easier. Not that the other methods wouldn't work, they all work. It's just sometimes if you want to drive a nail, I suppose you could drive it with a pair of pliers, but wouldn't it be easier to use a hammer? Again, if you want to screw in a bolt, I think you should use a wrench. I suppose you could use a pair of pliers, but a wrench is better. Some tools are made for some jobs. Now, what if they don't give you time or distance? Maybe they just give you forces and angles and things like that. Well, then you'd use Newton's second law. That's what you do. Okay, let's do another problem. Now, any questions so far? All right, well, let's do this one. Now, this is problem, we're going to do problem 19.7. It's on page 537. Let me find it here. 19, yeah, there it is. Now, in this problem here, on this problem 19.7, do they give you time, distance, or forces? What do they do? Well, actually, if you read the problem on page 537, I think they give you a force. So you might be tempted to use Newton's second law. But they give you time. Did you see that? They give you 3 seconds time. If they give you time, this is probably the method you want. The impulse momentum method. So we'll do that. Now you know the drill. The first thing you do is you draw a device sketch or a free body diagram in this class. So let me do that. There's our free body diagram. And the thing is, this has got an inner hub. It's got an inner hub. And there's a rope here. And there's another rope down here. A little bit messy there, sorry about that. Another rope down here, wrapped around that inner hub. Now this one's connected to some kind of wall connection there. And here, this is on a surface. This is 0.5 feet. And this is 1 foot. Now they give you that tension right there, and they said it's, they said that this tension is 50 pounds. I like my forces in red, so let me put 50 pounds right here. And I think I will put the weight on here. And how much is the weight? Well, if it's a 100-pound wheel, 100-pound wheel, oh, the weight's 100 pounds. That's what pounds are. Pounds are weight. Right? When you go on a diet, don't you want to lose some pounds? And I think your normal force will be equal to the 100 pounds. Now there's going to be a friction force down here. And that friction force, if you'll read it, is 0.1. See, the mu sub k is 0.1. So you can find this friction force. We'll just call it F for right now. There's your frictional force. I don't know whether it's going to the right or the left. Let's ask some of our really good students here. We're going to go to Jackson. Jackson, unmute and say hello, please, Jackson.
Oh.
Jackson, you got a 50-50 chance of getting this right. There's going to be some friction on this wheel here that has a hub, and there's some forces there. I didn't put the force that, you know what, there's going to be a force here too. Let's put that in red. I don't know what to call it. Let's just call it F. That'd be a good name. A nice name there. You got all these forces. But Jackson, we need to know if that friction's going to the left or to the right. What do you think?
It'd be going to the left.
Okay, now Jackson says it's going to the left. Jackson wants to put that force going to the left. Now let me think about this. I'm trying to make up my mind, Jackson. Let's see. You know what? I think Jackson's right. How'd you figure that out, Jackson?
Because the force coming into contact's going to the right. So it'd be acting in opposite of it.
You know, he's absolutely right. because this thing is slipping, it's putting a force on the horizontal plane here going to the right. And the equal and opposite force will be going to the left on the spool, like the wheel or whatever they call it. They called it a wheel. I agree, Jackson, it's going to the left. Now, as long as I got Jackson on the line here, Jackson, there's an ICZV someplace for this wheel. Where is it? Where is the ice? There is an ICZV. This thing is rotating, and it's rotating about a point. It's called the instantaneous center of zero velocity. But where is it, Jackson?
Would it be the center of the wheel?
No, see, if it was at the center of the wheel would just sit here and spin, and it wouldn't go anyplace. But this wheel is gonna travel down. It's going to go to the left, isn't it? Can you see that?
Okay.
It's going to go to the left, but it has an ICZV. Guess again, Jackson. We've done. Go ahead. Well, he didn't answer.
Not sure.
That's okay. We've done problems like this. This thing is unwinding. You see that there's this rope here, and this rope wraps around and around. Well, this is unwinding too. When you pull on this rope here, it's unwinding. And this rope here is unwinding. But this right here is the ICZV. Right there is your ICZV. Every point on this wheel, it's like rolling. See, if you have a wheel and it's rolling, you know a rolling wheel, if it's rolling down the street, or get a basketball and roll it down the street. It doesn't sit there and just stay in one spot and spins. It rolls down the street, and this right here is called the ICZV. Every point on that basketball at that instant is rolling about this point. See, if you take a point on the basketball here, you'll discover that it has a velocity like that. If you take a point on the basketball up here, it has a velocity like that. If you take a point up here at the top of the basketball, it has a velocity like that. And actually, that velocity there is a little bigger than that velocity there, because velocity is equal to r omega. Every point on the basketball has the same omega, but because this r is longer than this r here, the velocity of the top of the basketball is going faster than these other points on the basketball. But this point down here at the bottom at that instant has zero velocity. They call that the instantaneous center of zero velocity. Unwinding is just like rolling. See this point here, let's call it point A. This wheel is unwinding about point A. And that's, every point on that wheel is rotating about A. Like if you took a point over here someplace, That point has a velocity going like that. If you took a point up here someplace, that point has a velocity kind of going like that. I think it'd be a little bit bigger than that. We'll make this a little smaller. What about a point down here? Well, strangely enough, that point has a velocity. It's pretty small. But see, the whole wheel is rotating counterclockwise. So a point down here on the wheel, it has a velocity kind of going to the right. In fact, it's slipping. It's slipping. You've got kinetic friction. The force of kinetic friction is equal to mu sub k times the normal. In this case, if you read the problem, they said mu is 0.1. The normal is 100 pounds. So we know what the friction is. It's 10 pounds going to the left. Okay, well, look, we know a lot of stuff here. We know the friction and these 100 pounds and the 50 pounds. We don't know that force there yet. We're going to try to find it. What else are we supposed to find? They want the velocity of the center. Call this g. They want to know how fast g is going. Okay. Any questions so far? Well, all right. Did they give you some time? They said, yeah, 3 seconds. When they give you time of 3 seconds, guess what? You want to use impulse momentum, don't you? You want to use this one here. Now, this is I omega 1, but it starts from rest if you'll read it. So we don't have any initial momentum. So this is what we want for our equation. Now you can write this about point G, but I'll show you a shortcut. We should do it about point G. I think we got time. We got 22 minutes. There's a shortcut. You can write this equation about your point A. But there's a catch. The catch is point A has to be the ICZV, but it is. We found it. It's unwinding about point A. But in order to do that, we're going to have to find IG and IA. Now I'm going to shut up for a tiny minute, and I want you to find IG and IA. I'll be quiet. They give you enough information if you'll read it. Go for it. And then I'll call on the brightest of the brightest here in a little bit. And you guys are really good. I want you to find the mass moment of inertia about G and about A. I'm going to do it. I'll see if I can get it right. All right, go. You're going to have to read the problem, though. If you don't have a book, the radius of gyration is 0.75 feet. And we know it's a 100-pound wheel. I think you can do it. I'll be quiet and let you work for you. You have a minute and a half. Go. if somebody tuned in and they don't know what we're doing problem 19.7. It's on page 537. Right now, we're trying to find the moment of inertia about the center of gravity. And they give you the radius of gyration. We should be able to do it. You know how the equation goes. It goes m kg squared. Okay, you have another 30 seconds to finish up on that one.
Professor,
Yes.
I think you're working 19-17.
Is that Ashley?
Yes.
Ashley gets a honking thank you point. We are trying to work problem 1917 on page, I got the page number right, Ashley. I did get the page number right, didn't I? But it's not 19.7, is it? Thank you, Ashley. Hey, as long as I got Ashley on there, what'd you get for this moment of inertia about G, Ashley?
1.74689.
That's what I got. I'll just round it off. Now, Ashley, what are the units?
Is it slug feet squared?
Yes, good going. I really appreciate your help. Good going on that. Now on this one, you have to use the parallel axis theorem. And I don't have it yet, but I'm going to do it right now. Did anybody get 2.5233 slug feet squared? If you did, say uh-huh. I didn't hear
Yes,
any.
sir.
Was that a yes?
Yes.
Yeah, there's one. I need another one.
That's what I got.
Yay, good going. I tell you what would be fun to do is to do both of these. Now this one's going to be the easiest. Well, I don't know. Yeah, I think it'll be a little easier. It doesn't matter. One of these is going to solve our problem for us. Let me make a little room here and we'll do it. Here, we'll do this one. Okay, now what they're asking here is to take the sum of all the moments about G. Well, you got 3 different moments. See, this 50 pounds gives you a moment about G, and it's going to be 50 pounds times the distance to it, which is 0.5 feet. We'll do these counterclockwise. And then you have this force of the cord or the string here, but it's also counterclockwise, isn't it? It makes you turn the same way the 50 pounds does. So you would add that. You wouldn't subtract it, you would add it. It'd be F times, well, that's also 0.5 pounds, isn't it? But see, that little friction guy He's making you go clockwise. You're going to have to subtract it. 10 pounds times 1 foot. That's it. That's it for all the sum of the moment. Wait a minute. Wait a minute. Auga. I'm forgetting something terribly important. I'm forgetting the time. Well, what's the time? 3 seconds. Don't forget the time. We got the moments, but I forgot the time. Equals 1.7469 slag feet squared times omega. It's sad, but we have 2 unknowns. We can't solve it. Okay, we can't solve it. Now we could write this equation here too. Now let me think about that a minute. You know, I'm thinking about that equation there. I kind of like it. I think it's only going to have 1 unknown. Now let me write it. Now what I'm going to do now is I'm going to write this equation here. I just wrote this one. But now we're going to write the sum of the moments about A. Okay. Well, the 100 pounds goes through A. That doesn't give you a moment. And this 100 pounds goes through A. But the 50 pounds, it gives you a moment about A, but the distance is 1 foot from A up to the 50 pounds. And it's counterclockwise. We'll do everything counterclockwise. The F goes through A, so we don't need it. It doesn't give you a moment about A. But the friction does. And it's going clockwise, so you're going to have to subtract the friction times 1 foot equals the 2.5233 slag feet squared times omega. Oh, dang, we still got 2 unknowns, don't we? In fact, I don't think we've improved our situation much. We got 3 unknowns now. We have big F, we have little f, and we have omega. So it looks like we're in trouble.
Don't you know the friction?
There's only 1 friction. There's not another friction. What do you mean, Ashley?
The little f, isn't that the friction?
Yeah, little f is the friction, but big F is the force of this cord here pulling on it.
But is the friction 10 pounds?
Yeah. Oh, good thinking. Good thing. Ashley, was one of those yours already? Did you get 2 today?
I think so.
Wowie. She got 2 thank you points today. Good going, Ashley. We don't want to have an unknown there. We want to have 10 pounds. I really like that. That's going to be nice. 10 pounds times, okay, now I got myself lost again. But we're doing it about A. Well, it's a half. It's 0.5, isn't it? If you're doing it about A, the distance to the friction is 0.5. Yeah, that's right. The distance to the 50 is 1, but the distance to the little f is 0.5. Hey, I like it a lot. We can get omega now. Is there room? Yeah, there's barely. Take your calculators and plug in that equation for me and find the omega. Go for it. Oh, wait a minute. Wait. Ooga. What did I forget again? I forgot the same doggone thing again. What did I forget? I forgot the time. We're doing this equation here. What is the time? 3 seconds? Don't forget the time. Like I did. Okay, now I got it right. See, I left out the time. I just put the moment in there. It's not the sum of the moments. It's the sum of the impulses. You got to have the time in there. Okay, now solve that for your angular velocity. Go for it. Well, I did that. Let me ask somebody, see what they got. How about my friend, since Ashley's helped us so much, let's ask Ashley. Ashley, did you get the angular velocity of that wheel?
I got 53.5 radians per second.
That's what I got. I got 53.5 nothings per second. Now let's see if we got the right answer. This was 1917, and I'm going to see what they got in the answer book. The answer book says 26 point. Oh, no, they didn't want that. They wanted the velocity. See, this thing is going down the street. Here's the equation. V equals R omega. They ask for the linear velocity. See, this is the angular velocity. The linear velocity is going to be the 0.5. See, this is the ICZV. It's going to be the 0.5 feet times your 53.5 radians per second. I could almost do that in my head. 26.75. I did that in my head. That's kind of dangerous. Feet per second. Did I do that right? By Jove. I think that's what they got. If you look at 1917, well, they rounded off. The book got 26.8 feet per second. We got 26.75. They just rounded off. But here, let me show you one last thing here. We use this equation here. Let's do it with this equation here, okay? That'd be fun. See, the beauty is we could do it without equation and check it ourselves. We don't need no stinking answer book. We don't need no stinking answer book. We can check this stuff ourselves. All right, let me make some room here and we'll do it. We all know that this is dynamics. We're not going to erase those thank you points, though. Those students are very, very helpful to us. I think there's enough room to write this equation. No, this one. We're going to write this equation. We're going to take the sum of the moments about G. Gee, we only have 3.5 minutes. Okay, well, G's here. That 100 pounds doesn't give you a moment. Neither does that 100 pounds. But the 50 does. This time I'm going to remember my time. We got 50 pounds times 0.5 feet. I'll just put the time in now before I forget about it. It's 3 seconds, right? Yeah, 3 seconds. Now that's counterclockwise. You know what? We never got the F though. That's a problem. To do this, you're going to have to go plus F times 0.5 times 3 seconds minus the friction, which is 10 pounds. Oh, gee, I'm going to have to go around this here. Times, it's 1. From here all the way to the bottom, it's 1 foot times 3 seconds equals 1.7469 omega. And here's your equation. But the doggone thing is, do we have this big F? Uh-oh, we don't have the big F. How are we going to get that big F? Well, you could get it from here, yeah. Let me show you one last equation. We have 1.5 minutes. There's another important equation. We already used this one, so I'm going to erase it. I want to see if you recognize this one. You know it's going that way, so you got 50 pounds going that way. Minus, no, you got the 10 pounds going that way too. 50 pounds plus 10 pounds, those are both going to the left. Minus that F, which we don't know, times 3 seconds equals the mass in slugs times the velocity. We got the velocity. It's 26.75 feet per second. Now, my question to you is, what's the name of that equation? I know you've seen it before. What's the name of that? Wait a minute. Yeah, that's right. Did I do that right? No. This is not right. This is not right. It's 1.7469 slug. No, I had it right. It's 100 over 32.2. Yeah, but you'd have to put an acceleration in there. No, you wouldn't. No, you wouldn't. No, you wouldn't. No, that's still not right. Oh, gee. Here we go. There we go. You know what that is? I don't have time to ask you guys. We got to go. But that's the linear impulse momentum equation. See, this is the linear impulses, force times time, all right? And this is the I omega. That's the angular momentum. And the beauty of this equation is you can solve for F. Well, you've got two equations and two unknowns. And you can check it out yourself. And you can solve for F. Any last comments or questions for today? Well, you got some homework, and we'll continue on with this fourth method of ours on Monday. Okay, here's your chance to say something, because I'm going to push this red button. We studied impulse momentum today. Okay, bye-bye, students. I'll see you on Monday.
Bye.
Adios. Bye. Farewell for now. Be good.